Start sharing. You will record the session? Yes. So, Krishnan, do you want to introduce?
Hi. Okay, sure, I'll do that.
Yes.
Yeah, I'll start. Shall I?
So,
Can you hear me?
Krishnan, do you want to
Yes.
introduce?
I'm on my mobile. I'll just give me a minute. Yeah. So it's a great pleasure. Welcome everyone to this talk by Archna Kumari. She's completed her PhD from IIT Delhi and is going to speak to us about this work with Gaurav Bhatnagar and Michael Schlosser. So over to you, Archna.
Thank you, Krishnan. Hello, everybody. Thank you for coming for this talk. And I also want to thank the organizers for letting me speak here. So the title of my talk is I'll be talking about some results in weighted and elliptic enumeration. So this is a joint work with Gaurav Bhatnagar and Michael Schlosser. So this is the outline of my talk. I'll be starting with some basic definitions and notations. Then I'll be talking about elliptic extensions of Fibonacci numbers, and then I'll be discussing elliptic extensions of elementary identities, and then elliptic hypergeometric series. So in the literature, there are a lot of Q identities. So my objective is to study two types of Q identities. One is of hypergeometric nature, and the second is the combinatorial nature. So yeah, that is what we are going to do. So starting with elliptic hypergeometric series. So Gauss in 1812 work with hypergeometric functions. So there he defined hypergeometric series was defined as summation tk, where the ratio of successive terms tk plus 1 over tk is rational rational function of k. Then it is called hypergeometric series. For the basic, then Heine was the first one to find Q analogs of hypergeometric identities or results, and those were called Q hypergeometric results, Q hypergeometric or basic hypergeometric results. Then, so basic hypergeometric series is defined to be the summation tk, where the ratio of successive terms is a rational function of qk, and if the ratio of successive terms is a elliptic function, then we say the series is elliptic hypergeometric series. So this is one of the example of hypergeometric series. So this is a binomial theorem, where the coefficient n choose k is a binomial coefficient. So we have extension of this in Q hypergeometric series as well. So in the elliptic combinatorics, Schlosser and Misuyo have worked very rapidly in this area. So what we do here is we just count objects with respect to some weight functions. So we are just doing weighted counting here. So sometimes the weight could be arbitrary, and the weight could be elliptic weight functions as well. So I'll be talking about that. So in the first part of my talk, I'll be talking about the extensions of Fibonacci numbers to weighted and elliptic extensions. So we have given the proofs using combinatorially. So in the second part, I have we have extended elementary identities to elliptic numbers, and we have used a simple approach of telescoping to do so. So we have found extensions of these summations, so sum of first and odd numbers, then sum of cubes, and like that. Then we have extended some Q hypergeometric identities to elliptic hypergeometric identities. So I'll be talking about. So we found a technique to find elliptic hypergeometric expansion formulas, and as a result, we found some transformation formulas. So to begin with the first part, I'll start with what a Fibonacci number is. So we are defining Fn plus 1, the n plus 1 at Fibonacci number, to be the number of all possible tilings of n 1 cross n board. So we have this n length board, and we are placing, so square is a 1 tile and a domino is a 1 cross 2 tile. So we are placing squares and dominoes over this n board, and then we are counting all the possible tilings of this n board. So if you look at the last tile of this n board, so it has two possibilities. Either it could be a domino or it could be a square. So if it is a square, then we are left with the n minus 1 length board, and then the number of possible tilings could be given by Fn, the nth Fibonacci number. But if we have domino at the last tile, then we have n minus 2 length board. So the number of tilings would be given by Fn minus 1. So we have the recurrence relation, Fn plus 1 is Fn plus Fn minus 1. And for the n is equals to 1, so we only have a square, so the number of tiling is just 1. And for the 0, we have defined F0 to be 0. So we can also, if we introduce some weights, if we assign some weights to domino and square, suppose we assign a weight 1 and to domino weight q raised to power k, where the domino is placed at the position k comma k plus 1. So I'm assigning a weight q raised to power k to this domino, and then now we are counting the number of tilings of n length board. So for example, if you take a 4 length board, so this is a 4 length board, and the one possibility of tiling is just keeping all the tiles to be squares. Then second possibility is if we are placing one domino and domino at the 3 different positions at 1, 2, 2, 3, and 3, 4. Then we have 2 dominoes at position 1, 2, and 3, 4. So these are the all possible tilings of 4 length board. Now I'm defining a weight of a tiling to be the product of weights of all the squares and dominoes. So here in the first tiling, the weights given to each tile is 1 because all the squares. So the weight of this tile is 1 only. Then in the second case, the weight assigned to the first domino is q raised to power 1, and the weight assigned to second and third is 1 and 1. So the product of the weight is q raised to power 1, and then similarly q raised to power 2, q raised to power 3, and q raised to power 1 into q raised to power 3, which is q raised to power 4. Now we are adding all the weights of these tilings, so we are getting 1 plus q square plus q cube plus q4, which gives us the F5 at Q. So fifth Q Fibonacci number. So Q Fibonacci numbers are defined as a sum of weights of all the tilings, where the tilings are like this. So this is how we define the Q Fibonacci numbers. And so Q Fibonacci numbers appeared in the work of Schur. So Schur gave the proof of Rosers-Ramanujan identities, where the Q Fibonacci numbers as Q polynomials appeared. Then then there's a book called Proofs That Really Count by Benjamin and Quinn. So they have given a lot of Q analogs of identities, Fibonacci identities, and others. Then there's Garrett also worked in the Q analogs of Fibonacci identity. So she's given there's a paper of her which is unpublished, but it's on archive. Then Siegler followed the similar approach to find the Q analogs. Now, this is a specific weight we have given to a domino. If we give an arbitrary weight to domino, say WK. So now I am assigning a weight WK to this domino positioned at K comma K plus 1, and to square I'm just giving the weight 1. So now if we count the number of tilings of this n length board, then we call the Fn plus 1 to be the weighted Fibonacci number. So we are counting. So the weight of tiling would be the product of weights of squares and domino, and the sum of all the weights of tiling would be the Fn plus 1, n plus 1 at weighted Fibonacci number. And again, looking at the possibilities of last tile being square or domino, we can see that it follows this three-term recurrence relation. And for the n is equals to 1, again we only have square, so the Fn is equals to 1. Then we define m shifted Fibonacci number. So we are not placing dominoes in the first m tiles, and then we are placing dominoes in square randomly after m tiles. So these are kind of shifted by m tiles, and then we assign the weight same to domino. Then we assign the weight again to domino at position at m plus, say, K comma K plus 1. So now the recurrence relation. Okay, so this is the notation we are using for m shifted Fibonacci numbers. So Fn plus 1 superscript m denotes the number of tiles it's being shifted by. So the first one is 1, and for the 0th it's 0, and this is a three-term recurrence it follows. So this definition is modded by there's a paper of Garrett, Ismail, and Stinton. They proved M shifted Rogers Ramanujan identity. So this is motivated from there. So we have found a lot of Q Fibonacci. We have extended a lot of Q Fibonacci identities, and this is one of them. So this is Cassini's identity, and over the period of time, for these people, this is being considered for different extensions of this, and this is the full generalization of this identity. So in the if I is equals to 0 case, this is considered by Siegler and is given a combinatorial proof of this identity. So there's one more, so I'll be discussing proof of this one. So if we just so on the left hand side we have f of m plus n plus 1. So this is m plus n plus 1 at Fibonacci number. So we are counting the number of tilings of m plus n board. So if we count the number of tilings of this board in two different ways, then we get this. So there's a concept of fault. So fault, if we say fault at mth tile, so there's no domino at the mth tile, and then we'll denote. So there's no domino at the mth tile. So I'm considering if there's a domino at mth tile or there's no domino at mth tile. So in the first case, if we have a no domino at mth tile, so we'll split this board into two. So we have this first board of length m, and then we have this board, second part of this board as length n. So now if we count the number of tilings of this first board, it's just f m plus 1, weighted Fibonacci number m plus 1. And for the second part, it's being now shifted by m tiles. So we are counting it by m shifted Fibonacci numbers. So it will be f, because the length is n, so fn plus 1 and superscript. In the second case, when we have domino at the position m comma m plus 1. So the weight associated with domino would be Wm. So and now we will split this board into again two. So first we have m minus 1 and second we have n minus 1 length board. So the second part of the board is shifted by m plus 1 tiles. So it's fn power fn superscript m plus 1. The first one is just weighted Fibonacci numbers, so fm and the weight of the domino. So we have considered few Fibonacci. We have considered some Fibonacci identities and extended those to weighted Fibonacci identities. So there are some theorems like this. So now this we have done with arbitrary weight function, but we have also given a elliptic weight function. So to define an elliptic weight function, first we'll see some definition and then we'll give the elliptic weight function. So this is a modified Jacobi theta function. So it is defined as a infinite product of these two factors, where p is norm p and the parameter a is non-zero, and mod p is less than 1. So if you take p is equals to 0, the second factor vanishes and we are just remains with 1 minus a. So, and if we have more than one parameter, so we use this shorthand notation. There are some important properties of this theta function. So one of them is the inversion. So theta of a is minus a times theta of 1 by a p. Then we have quasi-periodicity of theta function, and then the last one we have three-term recurrence. This is a three-term recurrence relation. This is due to Weierstrass. So it is very helpful in defining elliptic function in terms of this specific expression. So what is an elliptic function? Elliptic function is a doubly periodic meromorphic function in complex plane. So this is due to Rosengren. So this says that we can write elliptic function in a ratio of modified Jacobi theta function, and this is a relationship of parameters which is called elliptic balancing condition. So this is how, if we just replace q and p with the e raised to power 2 I pi and e raised to power 2 I tau, then this is in doubly periodic with the periods sigma inverse and tau sigma inverse. So this theorem motivates to define elliptic function, give elliptic function like this. So this has some additional parameters a and b in addition to q and p, and this is again a ratio of modified Jacobi theta function. So it is a elliptic function, and yeah. So we can
Can I interrupt for a sec?
Yeah, sure.
Yeah, so the previous slide, the theorem is classical.
Yeah.
This theorem is classical. It's in, but Rosengren has a set of notes where this theorem is proved. So the theorem is known. It was in Whittaker and Watson, I think.
Yeah, right.
Okay.
Right.
So, sorry, go ahead.
Yeah. So this is the elliptic weight function we have given. So with respect to this, the associated Fibonacci number is the elliptic Fibonacci number. And since they are sorry, so we can further specialize the parameters and can find the special cases of this weight function. So if you just take p is equals to 0, the theta function reduces to the linear factor 1 minus aq and so on. So in the case p is equals to 0, we have 1 minus AQ and all the linear factors in numerator and denominator. So yeah, so if further we take B is equals to 0 and A is equals to 0, and then finally if we take A and B both 0, we get the Q weight, Q raised power K, and the corresponding. So in all the cases, the associated Fibonacci numbers is called, so this called ABQ analog, and the ABQ analog of Fibonacci number with this weight associated. Second, when we take B is equals to 0, so this is AQ analog of Fibonacci. The associated Fibonacci number would be AQ analog of Fibonacci number, and so on. So this is what we have done in Fibonacci. So the second part of my talk is about extensions of elementary identities. So so the motivation, so we define a Q number to be the ratio of 1 minus Q raised power n over 1 minus Q. And if you take the limit Q to 1, so this reduces to the number n. This is how we define the Q number. So m plus nq is m sub q plus q raised power m and q, which is this factor. Then this reduces to q raised power m plus 1, which you can write again as like this. So we have m plus nq is same as n plus nq. So this is what motivates the definition of elliptic number. So this first relation is due to the Weierstrass addition, Weierstrass three-term recurrence formula, and this is the elliptic number which was defined by Schlosser and Yo, and this is elliptic in log A and log B and B. So if you take Z to be 0, so it reduces to 0, and if you take Z to be 1, so everything gets cancelled out and it reduces to 1. If you further take P to 0 and A and B to 0, it reduces to the Q number n. So this is elliptic analog of number n. So initially we use the technique of telescoping. So we actually discovered a lot of identities using the technique of telescoping lemma, and then we proved the Fibonacci identities using the combinatorial means. So this was Euler's telescoping lemma, which was given by Euler's, and then we have used this alternate form of telescoping lemma to prove the elementary identities. So the first one is the sum of odd numbers, and this is the elliptic extension of this identity. So if you see that if you ignore this factor, like when we take P is equals to 0, P is equals to 0, A is equals to 0, this goes away, then this reduces to the number K plus 1, this reduces to 2 and minus 1. So we get 2K plus 2 times minus 1. So this is essentially what this identity is. So we can further take special cases of these, and if we take P is equals to 0, we get the weight function reduces to the ABQ, and the number reduces to the ABQ analog of number. So this is called the ABQ analog identity. Then we can further reduce it to AQ analog, and then BQ analog, and then Q analog. So, and we can also take other special cases, like we can take A to infinity and A to 0 and B to infinity. So we get a lot of Q analogs of elementary identities, and we also discovered some of Bernard's Q analogs of. Then we have two more And these were the elementary identities. Then we got, this is the second one where we have sum of rising factorials, and this is the extension in terms of elliptic numbers. So again, if you just ignore these factors, take p is equals to 0 and ab to 0, then and q to 1, so we get m plus 1 and so on. So this is an extension of elliptic. Then we have one more. Then we have one more where the rising factorials come in the denominator, and again this is extension in terms of elliptic numbers. So these were the elementary identities we have seen. Then we have one bit complicated looking identity. So as you can see, there are a lot of parameters other than K, so C, D, G, H, K. So this is just the left hand side of the identity. Then this is the right hand side of it. And again, we discovered this using the technique of telescoping. So in the P is equals to 0 case, this is just an elementary identity, but it looks a bit complicated. So this has a bit strange factors. So here we have factors in terms of q raised power quadratic factors, but normally we have factors in terms of q raised power k. This is a bit strange. So the third part of my talk is elliptic hypergeometric series. So yeah, I'll be starting with again some terms. So we define q-shifted factorials. So q-shifted factorials are defined to be k factors, and then we define infinite. So using this notation, we can write Jacobi theta function as the product of AP infinity and P by AP infinity. Then we define the QP shifted factorials as this product of Jacobi theta function. And again, if we have more than one parameters, we use the shorthand notation. So this is one example. This is how a very well poised elliptic hypergeometric series look. So the notation is for very well poised, and this is how it is defined. So it's called very well poised because of this part, and this is how. And there's the terms very well poised is just to say because of the relationship between the numerator and denominators parameters. So this is one of the fundamental results of elliptic hypergeometric series. So Frankel and Ture gave this and this is an extension of 8phi7. So if you take p is equals to 0, it will reduce to Jackson's 8phi7 sum, and if you further take q is equals to 1, it will reduce to Dugal's 7f6. And there was one more. So he gave two of the most fundamental reasons. One is this, and the second is 12p11, which is the special case of which is like the Q geometric case of which is 10p9 transformation. So this is one of the expansion formulas we have found. So it has three parameters aj on the both sides, and if we specialize aj to delta function, then this sum just goes away, and this sum also goes away. So this reduces to the Frankel and Thure's 10b9 summation formula. And we can also find we can also find Frankel and Thury's 12v9 from 12v11 transformation from here. So if we take AJ in a manner that this inner sum is summable by elliptic 8c7, then the resulting transformation is a 12v11 transformation. So how did we find the expansion formulas? And this so these sorry. So the technique we used, we found out later that it is closely related to the well-poised Peary lemma. So first, how do we say a pair is a Bailey pair? So we define a Bailey. So alpha and beta are two sequences called Bailey pair if beta n can be written as summation k0 to n fn k alpha k, where f is this particular matrix. And if the matrix is changed to this one, then it would be called the well-poised Bailey pair. And this matrix is due to Bressud, and it has some specific terms which keep keep arriving in our expansion formulas. So well-poised Bailey lemma. So given a well-poised Bailey pair, well-poised Bailey lemma gives a new well-poised Bailey pair. So this is a well-poised Bailey lemma, and the elliptic extension of this is given by Spreadinov, and there are analogous results of same kind which were given by Werner. So we used a lemma to find the expansion formula. So this is a key lemma, and we are using the finite version of this lemma given by Bhatnagar and Rai. So if we have a pair of inverse matrices and a matrix H, then this summation is equals to this summation. So, and this can be proved by just interchanging the summation on the right hand side twice. And the pair of matrices we used is due to Werner, and if you take P is equals to 0, the matrices reduces to the Bressud's matrix, which were being used in the well-poised Bailey lemma. So what we are doing is we are just choosing H in a manner so that we can sum this inner summation using some existing summation formula. So the first expansion formula we have found is by summing this inner sum by Frankel and Thury's sum. So we choose H, we take H and J as Hj and Km, and Hj is the matrix F, but K is a free parameter, so we can like choose the terms as per our need, and we can make it convert the inner summation into some existing summation formula. And yeah, so we modify Hj for better looking terms. And the first expansion formula we just saw is equivalent to Spreadinov's elliptic well-poised Peary lemma. Then this is how this is related to well-poised lemma. So the left-hand side, so in the well-poised Peary lemma, we saw that we have beta is equals to P alpha. So this beta is our left-hand side, and this P alpha gives our right-hand side, where B is the again Bressud matrix. Yeah, so we sum the inner sum using different summation theorems, some due to Werner, two summations due to Werner, and one of Lee, Raines, and Werner. So, and we got 3 more expansion formulas. So 2 are equivalent to 1 are Bailey-Lemma type results, and 1 is a new expansion formula. So this one is the new expansion formula, and this we we found by using Lee-Rains and 1R. So since we have the parameter AJ here, so we can just choose AJ in a manner so that we can sum this inner summation. We'll try to sum it using different summation theorem, which we did not use in finding the expansion formula, and then we find the transformation formula. So using these summation formulas, we have found 8 new transformation formulas. So I'll be showing one of them. So this is one of the transformation formulas. So yeah, and then there are 7 more, so I'm not going to show here. Then we considered the special cases of these transformation formulas. So for example, for this transformation formula, if we take Q hypergeometric case of this, if we take P is equals to 0 in this one, so we get this transformation formula where the left hand side is a very well poised and balanced 12v11 series, and on the right hand side we have a 5v4 which is nearly poised. So this is a transformation formula which looks like Bailey's formula and 2 of Andrews and Berkovich, but we did not find it in the literature. Then again, if we specialize here C and D, then we get the 2 summation formulas. Again, these look like special cases of Bailey's transformation, but we could not find these as well. So the summary of my talk is that we have talked about, we have found elliptic extension of elementary's identity, and then we found the elliptic extensions of weighted and elliptic extensions of Fibonacci number, and then we have talked about elliptic hypergeometric series, and we found some expansion formulas and transformation formulas. They could be so in elliptic combinatorics, there a lot of work has been done by Schlosser and Hugh, and there could be more that can be done. So, and same in the elliptic hypergeometric series, we can extend this to multivariable keys as well. So these are the publications. Thank you so much.
Okay, thank you very much. I don't know, any questions or comments?
Yes, maybe I can ask. So right now you're working on multi-dimensional extensions of these identities from the last section you discussed?
Yeah, like we have considered not, yeah, we are considering.
Okay, so type A and type C extensions, like related to the Milne type of series, correct?
Yeah.
But that's a quite ambitious program,
Yeah, it is.
Yeah.
Yeah, so let me comment on Michael's question. So I don't know how many calculations you've done, but I think the issue is that they're not there's only one or two. There's one summation theorem which is there in multivariable case, which is none of these guys.
See,
Yeah. So if there is any chance of anything happening, it will happen only from there, right?
that CN type result.
Yeah. So so I don't know how much you have done the calculations yet, but I guess that's one thing to check out.
Yeah.
Okay. Thank you.
Okay. Thank you.